Welcome back. In this section, we'll be looking at radicals, which are another word for expressions involving roots, and we'll also be looking at rational exponents. What happens if we have a power that's a fraction? A couple of things just to remember from before. The first is that if we're talking about roots, if it's an even root, a square root, a fourth root, a sixth root, that's only going to be a real number if the number that we have inside the root is not negative. So if somebody says square root of 4, that for sure is a real number. Square root of 0 also would be a real number, but something like square root of -3, that would not be a real number. For odd roots, on the other hand, we can have them whether the inside is a positive number or if the inside is a negative number. So, for example, we have here cube root of 8 is equal to -2, and the reason I know that is because if I were to take -2 and multiply it by itself 3 times, or -2 times -2 times -2, three negatives multiplied by each other would give me something negative, and 2 times 2 times 2 would give me 8. So in other words, I know that -2 cubed gives me -8, so that means cube root of -8 must be -2. And of course, you could also have cube roots of positive numbers. So if it had been +2 cubed, then it would be a +2 times a +2 times a +2, which would be +8. So the cube root of +8 would be +2. We've got, just like we did for exponents, some properties for rational expressions, and some of these are similar to the ones that we had for exponents. For example, for exponents, we had the property of what if you had two things multiplied raised to a power, and that would be the individual factors each raised to that power. We also had one for what if we had a quotient raised to a power, and that would be the numerator and the denominator both getting that power. And you'll notice we've got similar sorts of properties for radicals. If you have two numbers or two things being multiplied inside of a root, well, then we just have the roots of those individual things multiplied together. Or if we have a fraction inside of a root, well, that's just the root applied to the numerator as well as on the denominator. Property number 3 is also kind of a nice one to know. This is as long as our root exists, so as long as we're not taking the even root of some sort of negative number, then it doesn't really matter whether we do the root first or the power first. And that can be really useful, and we're going to see some examples of that later on, where maybe it might be easier to do the root first and then do the power later versus doing the power first and then doing the root later. The last property is sort of a minor one, and it's one that I'm not going to dwell on too much, but it's a good one just to know for in the future. And this is if we're talking about looking at taking a root and a power, and it's the same kind of root and power. So, for example, cubing and then cube rooting, or fifth power and then fifth rooting. If we're talking about some sort of an odd power and root, well then good for us, they undo each other perfectly. So if you had something cubed and then cube rooted, the two things will undo each other. We have to be a little bit cautious here, though, when it's an even root. You'll notice that I say if you have something to the power of n that then gets an nth root on top of it, that instead of being just the a itself, it gives you absolute value of a. And the reason for that is actually based on the power itself. If a was a negative number and you raised it to an even power, whether you're squaring it or raising it to a fourth power or raising it to a sixth power or whatever we're feeling like doing, we're going to get something positive that comes out. And when we take our root, we'll get a positive that comes out of it. So it doesn't matter if the inside was negative to begin with or positive to begin with. Because we're raising it to an even power, we're going to get something positive out of it, which means that, yes, they'll sort of cancel each other out, the root and the power, but it won't give us our original number back. It will give us the absolute value of our original number. course, if we're dealing with variables and we make an assumption that the variables are going to be positive all the time, then we don't have to worry about that absolute value. I mostly mention this now because in the future, and this is especially if you're taking calculus in the future, there are a couple of examples that pop up where suddenly there's a surprise absolute value that appears, and usually the answer for why did we suddenly have an absolute value appear in our answer is usually because of that, because there was some sort of squaring followed by square rooting, or fourth power followed by fourth rooting, and that gave you something that was guaranteed to be positive. So absolute value was there. One other little caution just to mention before we go on, and it's this. You'll notice that we have properties for things that are multiplied or things that are divided inside of a root, but we don't have a property for things that are added or subtracted inside of a root. And in fact, in general, it is not true. So if you have two things added inside of any kind of a root, it is not the same thing as the individual terms, each themselves inside of a root. So unfortunately, that is not the case. So if somebody says square root of 4 plus 5, that is not the same thing as square root of 4 plus square root of 5. So when we look at simplifying expressions that involve radicals, it's still kind of a follow-on to what we did before. We need to reduce the number of terms that we have, reduce the number of symbols that we have, leave only positive powers, and we have some further complications here. So if we're dealing with things that have radicals, we want to make sure that there's no fractions inside any of our roots. So something like square root of a half, that would not be in simplest terms. Even if you used the property from the previous page and rewrote that as square root of 1 divided by square root of 2, that still wouldn't be in simplest terms because of the second thing that we want, which is to have no roots in the denominators of our fractions. And even if we don't have any fractions at all, there's still something for us to consider, which is to make sure that we don't have any perfect nth powers as a factor inside of our nth root. Since we're mostly talking about square roots in this class, then really what we're saying is we don't want any perfect squares as factors inside of our square roots. So something like, for example, square root of 32 is not something that's in simplest terms yet. Even though 32 isn't a perfect square on its own, it has a perfect square that goes into it. Since 16 is a perfect square and 16 goes into 32, then too bad for us, root of 32 is not in simplest terms. This is also the case for things that are variables raised to powers. So something like x cubed inside of a cube root, that's also not in simplest terms because x squared is a perfect square and x squared does go into x cubed. So for us, that means that there'd be further work for us to do. So what we're going to do here is we're going to simplify things as much as possible, reduce the number of symbols as much as possible, leaving only positive powers, no perfect squares as factors inside of square roots, all of that good stuff. So for the very first one that we have, square root of 40x cubed, there's two things for us to notice with this, and that is that we have two different perfect squares sort of hidden inside of this. One of them is 4, which happens to be a factor of 40. So I'm just going to rewrite this for a minute here. I'm going to rewrite 40 as 4 times 10. And x cubed is also has a perfect square buried inside of it. X cubed is x squared times x. And now what I'm going to be doing here is using my property that we had from a couple of slides ago. The property was that if we have some things that are being multiplied together inside of a root, then I can just take each of those individual factors and put them inside of roots. So here, for my example that we're looking at, we have 4 different things inside of a root. So I could say, well, that's the square root of 4 times the square root of 10 times the square root of x squared times the square root of x. I'm going to be a little bit more clever about it, though, because I know that some of these things I'll be able to get rid of my perfect square, and some of them I won't. So what I'm going to actually do is square root of 4 and square root of x squared. I'll write those up first because 4 was a perfect square and x squared was a perfect square. But the 10 and the x, neither of those are perfect squares, so those are going to both stay inside my square root. So I have now square root of 4, which is 2. I have square root of x squared, which is x. And then left inside of my square root is 10x. One little other side note, which you might be noticing here. I had a square root of a perfect square, and I'd said on the previous slide that if we have a square root and a perfect square, we should get some sort of absolute value going on. And you might have been wondering why I didn't put an absolute value on. And part of that is kind of buried in the example itself. It says just to assume that any of our variables that we have only take on positive values. So since we're assuming that x is a positive number to begin with, then we don't need to put an absolute value sign on top of the x. If I hadn't said that, if x was potentially a negative number, then I would have to put an absolute value sign on that x when I take it outside of the square root. But that's, again, something that we're not going to be really seeing much of in this class. Okay, example B, same sort of a thing. We've got a bunch of numbers all inside of square roots. None of them are perfect squares on their own, but they all have perfect squares that go into them. 75 is 25 times 3. 20 is 4 times 5. 12 is 4 times 3. And 45 is 9 times 5. We're only looking at perfect squares, and the reason for that is when we split things up, for example, the first term, it'll be a square root of 25 times a square root of 3, and one of those, the square root of 25, will turn out to just be a nice whole number. If I split things up into two numbers that aren't perfect squares, so for example, suppose I had decided to say instead of 12 being 4 times 3, suppose I had decided to say that 12 is 2 times 6. That would not be helpful because I'd be left with square root of 2 times square root of 6, and neither of those happen to be nice integer values. So remember that when we're simplifying these roots, we're only looking to rewrite them in terms of some sort of perfect square times something else. That's how we'll simplify them. So root of 12, I look for perfect squares that go into 12, and the only perfect square happens to be 4. So now I can split things up. I've got root of 25, which is 5, times root of 3. I've got root of 4, which is 2, times root of 5. I've got root of 4, which is 2, times root of 3. And I've got root of 9, which is 3, times root of 5. I'm not finished yet, though. You might also notice there are some terms that are similar. I've got two terms involving roots of 3s, and I've got two terms involving roots of 5s, and those two terms can be combined together. 5 root of 3 plus 2 more root of 3s gives me 7 root of 3s in total, so I have 7 root 3. And I have 2 root 5s and 3 more root 5s, which gives me 5 root of 5. And that's as far as I can go. One term is in terms of roots of 3s, the other one is in terms of roots of 5s. Those are different roots, so unfortunately I can't combine those two terms. So I've gone as far as I can in simplifying that last expression. Okay, so this one, if we're taking a look at it, I have nothing really for the individual roots that need to be simplified. However, you can see that I've got a two-term expression multiplied by another two-term expression. So for part of my work in simplifying this, I'm going to have to multiply everybody out. That means that everything from the first bracket will need to multiply by everybody in the second. So the 2 root of 3 will need to multiply against the 5 as well as the other 2 root of 3. The negative root 2 will need to multiply against the 5 as well as against the 2 root of 3. So I have 4 little products for me to do. When I do the multiplying, I'll be multiplying the whole number parts together and the roots together. So for example, when I start off, I'll do 2 root of 3 times 5. And when I do that, I'll multiply the whole number parts together. 2 times 5 is 10. And I have only a single root, the root of 3, so root of 3. When I multiply 2 root of 3 times 2 root of 3, I'll have 2 times 2, which is 4, and I'll have root of 3 times root of 3, which is root of 9. When I multiply the negative root of 2 times the 5, I only have one whole number part and one root part, so I'll have a negative 5 root 2. When I multiply the negative root 2 times the 2 root of 3, I'll have a negative 2 for the whole number part, and for the root part, I'll have root of 2 times root of 3, which is root of 6. There's one little last thing for me to do here, and that's with the second term. You see I've got a 4 times root of 9, but of course root of 9 is the same thing as 3. So really the second term is 4 times 3, which is the same thing as 12. So I'll rewrite this 10 root of 3 plus 12 minus 5 root of 2 minus 2 root of 6. And you'll also notice there's nothing else that really can be done here. The root of 3, root of 2, root of 6, those roots are all in simplest terms. There are no perfect squares that go into those. And they're all 3 different roots, so there's no way to combine those terms together. So that's as good as that last expression can get. For this one, for D, I'm taking a look at this and I can see there's a bunch of problems. So number one, we've got a fraction inside of a root. We definitely don't want that to happen. And I did say earlier that fixing it by rewriting it as root of the top over root of the bottom doesn't really fix the problem, because now we'd have a root in our denominator and we'd have to still fix that. So one thing you might notice here, and this is kind of the same thing as we saw in the last section, maybe it might be easier to simplify inside first. So for example, instead of dealing with the root at all, I might decide to start off by simplifying the 24x to the 4y cubed over 3x. I might decide to do that first. Because if I simplify that and make that no longer a fraction, then I'll no longer have a fraction inside my root. So that's my plan here. I'm going to start off by saying, well, I have 24 divided by 3, which is 8. I have x to the 4 divided by x, which is the same thing as x to the 1. So that would give me x to the 4 minus 1, which is x cubed. And then I'd have the y cubed left over. So now, kind of the same thing as the very first example, we have some perfect squares that are buried inside that. I know that for 8, there's a perfect square of 4 that goes into that, 4 times 2. For x cubed, x squared is a perfect square that goes into that. X cubed is x squared times x to the 1. And y cubed is also a perfect square buried in that. It's y squared times y to the 1. And for the things that are not perfect squares, the 2, the x, and the y, those are going to be left inside of my square root. So the 2 and the x and the y will be left inside, and the 4, the x squared, and the other y squared, those will all leave my square root. I'll have square root of 4, which is 2. I'll have square root of x squared, which is x. And I'll have square root of y squared, which is y. So I'll have 2xy times the square root of 2xy.